Okay, we're going to start HTTP now. So we finished the data link layer, the network layer, the transport layer, and now we're up into the web protocol, or the application layer. We're only going to do two protocols. If I could have you pay. If we're only going to do two protocols. We're going to do HTTP and DNS. Which are basically the main two that all of us should care about. So we'll start with the basics, just in case you haven't had a web browser before, which is rare. But I'm going to go through some terminology just so that we know what we're talking about. A web page consists of objects addressable by a URL, and it can be an HTML file, a JPEG file, a Java applet, or an audio file. And it's bound to a host name. So the naming scheme that we have come up with for the web is to have the very first part specify a DNS name, a host name. There could have been other naming protocols that would have decoupled the IP address from the content, but we didn't do those. We have this where the URL specifies a host name, an IP address basically, and then some relative path name on that host name. Okay. HTTP is the transfer protocol that we use to transmit objects over the web, hypertext transfer protocol. It's the application layer protocol that the web uses. The idea here is you send a URL from the client to the server, and then the server will return content from itself to the client over a TCP socket or TCP connection. These are the RFCs that those two versions of HTTP are defined upon. So again, you have a browser sending a request, an HTTP request, formatted in a specific way, which we'll talk about. And then the response is on the same TCP connection, and that is also formatted in a very specific way. So it uses TCP, and it establishes a bidirectional TCP connection, and it allows TCP to do all the retransmission and the integrity and all the reliability and the congestion control, all of that stuff. It just says, you know what, TCP, you're good at that, you just do it. I just need a byte stream from myself to the destination, which is what TCP is really good at. The server, the web server, accepts any TCP connection attempts from any client. So any connection that goes to port 80 on the server will be routed to the web server listening on that port. And then HTTP messages are the things that are exchanged from the client and to the server. And these messages, they were explicitly defined to be encoded in text, fortunately, because nobody likes parsing a binary protocol. Like when you are looking in your web browser and you're like, give me the HTTP headers, it's good that they're in text because they could have been in some kind of crazy binary format that you wouldn't have been able to read. So it's a readable format, and this is intentional. A lot of internet protocols are text protocols that you can read. Okay. The last thing is that typically the TCP connection is closed after the transfer happens. Okay. There are two types of HTTP messages. There's the request message and the response message, and they each have their own format. The request message looks like this. You have the very first line is the request line, and there is a method, so it's a verb, that says, I want to get, in this case, get something, and what I want to get is specified in the next parameter, so space-delimited parameters, and this is the relative path on the server that I am looking to get. So in this case, it's the second half of the URI. And then I'm also going to specify the version of HTTP I want to use. So in this case, 1.1. This is followed by a set of HTTP request headers. So these are headers that allow the client to specify different things about the request that the server should know about. So in this case, it says, you know, the host that I want you to get this content from is www.someschool.edu. And that's part of the URI. And the reason why we want to specify this is because that web server could be serving requests for multiple websites. It could be hosting a dozen websites. And when you give it this request method, it needs to know which of those dozen websites that you actually want that path from. And that's specified in the host header. This is a required header in HTTP 1.1. That must be there. The rest of these can be optional, but that one is mandatory. Another thing that you send is your user agent. What is the version of the web browser that I'm using? And this is helpful because if you get a web request from a mobile client versus a desktop client, you might want to give back something different. And this is the way you can select on the server. If the server parses these request headers, this is the way the server realizes the kind of client that it's running with. Or more often is the case is like, is someone still using Internet Explorer? Or is someone using WebKit browsers, which is everybody else? And if they're using Internet Explorer, I better give a really dumb site back. And then if I'm using something modern, I would give the good stuff. So that's the idea. Another header, which we'll talk about later, is this connection header that says, what do I want to do with the connection after I'm done transferring? In this case, I'm going to close it. There are headers for localization. So I want all of my content in French. I'm in France. I speak French. I don't want English websites because I don't like the English. So I'm going to say only accept French. And if the website can't provide me French, then I'm not interested. And it'll give me a French site. So you could go to google.com in France, and if you have specified the language to be French, it'll send you to google.fr. And it knows, oh, you want the French version of the site. Okay. And then 2 carriage returns, because this is a GET. You don't want to send anything else, just this request. And then a blank line says to the server that you're done. I can actually process this request and send you back whatever you asked for. Okay. In response, a response message is sent from the server back to the client. It also has a status line, which has the version number and a response code. And the response code is either in the 100 series, the 200, the 300, the 400, or the 500. If it's in the 200s, that means everything's good. It's okay. And this is a verb that gets sent back. If there is an issue with access control, so say, for example, and you'll get this a lot on my sites because I'm not good at updating permissions sometimes, it'll say access denied. Those are the 400 level errors. If the server somehow has an error and crashes, those are the 500 messages. So HTTP has defined these status codes that are in the different 100 ranges to give you an idea of what happened on that request as a status. Some of the response headers, and so the HTTP response headers, they have the same format. There's this header that's followed by a colon, followed by the value of that header. So it's like a key value format. So it has the same format as the request header, but the request headers and the response headers are typically different. Like, it doesn't make sense to have, for example, the server header as a request header, because that's only relevant in the response. So a different set of headers are used on the way back. So the server software being run. So in this case, it's a super old Apache version that might have vulnerabilities in them. So this is what a bad guy would use to be like, oh, I'm going to run the latest exploit on this web server and own this machine. So that's what we call fingerprinting. So this would fingerprint the version of the software that you're running. There's headers that say, well, when was the last time that particular file has been modified? So that maybe I don't need the whole thing. Like if it hasn't been modified since the last time I retrieved that file, then maybe I can actually not retrieve that file. It just tell me it hasn't changed. And then I save network bandwidth. The content length of the payload I'm sending back, so I know how big this data is. And then the type. Is it an HTML file? Is it a JPEG image? What is the client-side handler that needs to run for this particular file that I'm sending back? And so this is how a web browser knows not to render your HTML as a JPEG image, right? It's like, oh, it's text HTML. I'm going to run the HTML renderer. Or it's a JPEG, image/JPEG. I'm going to embed that as an image inside of the page. So that's the content type part of this. And then this is followed by a new line. The headers are followed by a blank line, and then you get the data. Whatever the data that is being sent back is sent in the next line. Okay, there are a whole bunch of headers, and we're not going to cover all of them. There are caching headers, there are session management headers for cookies, there's authentication headers, there's tracking headers that allow websites like Facebook to figure out every site you've been on. There are localization headers, which we already talked about, content encoding headers to specify the type of the content you're getting. All of that stuff is not going to be covered here. That's all in the networking class and then the web security class for some of these ones up here. The thing that we're going to talk about are the headers for managing the connections. And this is important because this actually is going to determine how you develop your applications, for example. Yeah. Why is that not allowed? Oh, why is that even allowed? I haven't heard of cookies that don't expire, but yeah, you could have as misconfiguration just have a expiration date that's well into the future. If you're Facebook, why would you want your tracking cookie to expire, right? I want you. There are applications for being like people who want to track you don't want their cookies to expire at all, ever. They don't want your browser to throw it away ever. They want the same cookie so that they can track your sessions over long periods of time. Maybe that's why they do that. You can install a cookie cleaner or use incognito. Like if you do an incognito window, you get your cookie store is completely gone. So yeah, that if you really there are some browsers. Brave is the browser that will aggressively get rid of that stuff. That's actually more of a security. Yeah, web security would be what I would refer you to. Password auto login is built into some browsers. Yeah. Well, it depends on how the auto login is done. If it's password fills, there are some plugins for the browser, and then there's actually the native password manager. But if you're talking automatically, like Amazon, for example, has a cookie there that is bound to you personally that hopefully they don't want that thing to be deleted at all. And then they have a separate way of authenticating you, a separate cookie that authenticates you for purchases. Because they always want to give you a personalized page. So, but they don't want you to just, anyone with that personalized page should make purchases. They want to actually add another, and that also, web security. I'm offering that next quarter. I might as well plug my course since I'm going to offer it. That's what I'm offering next quarter. After this, yeah, actually that would be a good thing to take after, if you're really interested in this stuff. Yeah, all right. That wasn't a planted question for me to advertise my course. Okay, so this is how HTTP 1.0 works. And the way it worked initially was to have serial, non-persistent connections. It means one request and one response per connection. This was because it was the simplest to implement. Like if you had to implement this thing as a project, maybe in your networking class, then it's very simple. It's a very simple control loop for you to get a request, do the response, terminate the connection, and then go back to the beginning of your loop, right? So that's what we did initially. The issue with this implementation is that it was slow. So if the round trip time is RTT, then the amount of time to get some content back from the server is going to be at least twice the round trip time plus the transmission time of that object. And you can see that here. The first thing that has to happen on this connection is a TCP handshake. So one round trip time to get the first SYN-ACK pair, another round trip time to put the request, get the request to the server, and then the server will basically come back with the data. So this is 2 round trip times, plus the time to actually transmit the file. That's a long delay. I would like that to be smaller, if possible. Moreover, if I've got a couple of these things, so I have a web page and it's got like 10 embedded images in it, all served by my server. This is what happens with HTTP 1.0. I have the client, I do a round trip time, I do a handshake, I send the URL, I get the acknowledgement back, the server sends the data back, and then closes the connection. So now I've gotten the base page, but now I need to, and then I close the connection. So that's what this thing is. So this is an entire multiple round trip times to get the base HTML page. And then what I need to do is I need to get the embedded images. So I'm gonna have to do this all over again. I have to create a 3-way handshake. Well, I parse the HTML, and then I know I have to go right back to the server and get a bunch of images. I have to redo this again. I have to do a handshake, to send the request, and then the server reads the image from the disk, sends it back. Look at all these round trip times to get a base page and an image. So at least 4 round trip times plus a transmission time. So this is a problem. The image doesn't arrive until here, and usually when you visit a page, the page would like to understand the dimensions of every image that it's going to have to render so it can actually build a frame properly, and then it will fill in the images as it gets it. But in this case, it's taking you all of these round trip times to get the first part of the image, so you can't render anything unless your HTML specifies bounding boxes for all the images on that page. You can't render anything to the user initially. So this is a problem. This is what you want to get rid of. So multiple embedded objects on a page cause a whole bunch of connection setups and connection setup latencies to be incurred. You have all of this unnecessary load. So the server and the network are getting hit by connections over and over again from you, right? I just wanted one web page, and I'm ending up with a dozen connections to that server. There's got to be a better way. And then we also saw that these short transfers are really hard on TCP. If there's a packet loss that happens on these transfers, you're timing out. So that's also bad. So Netscape in the early 90s was like, okay, we got to do something else. So the idea of Netscape is, you know what, I'm going to use a bunch of concurrent connections from the client to the server, and I get a whole bunch of objects down at the same time. So that's what they decided to do, and this improves latency. So rather than wait multiple round trips times to get the second image, I'm going to just, in parallel, get all 10 images. I'm going to put all 10 requests, well, 8 requests actually. They maxed out at 8. So maybe the embedded HTML I get with one set of round trip times, but then I'm going to parse that HTML. I'm going to see that there's 8 embedded images. I'm going to create 8 simultaneous TCP connections to the server, and I get all those images in parallel. So that's what they did. This is bad because, yeah, you know how we were doing congestion control? And if one browser is using a single connection for all of this, and all of a sudden it's competing with a Netscape browser that's doing 8 at a time, well, guess what? You get 1/8 of the bandwidth. So that was slightly controversial. And I think you can still configure this on your browser, the number of simultaneous connections, although there's a better way of doing this that we'll get to later. Okay, one of the things with this approach is that it doesn't improve response time all the time. So for example, if sending 8 parallel TCP connections causes the server to fall over, then you've hosed everybody, including yourself, right? You could have gotten it done faster had you just done maybe 2 at a time. So there is this thing of diminishing returns when you start to do this. There's way more operating system overhead to deal with for each TCP connection. So this is where we went to HTTP 1.1, and this is persistent HTTP connections is the default in 1.1. The idea here is that the server is going to leave the connection open, and then it's going to wait for another response or another request from the client. And so the client, if the client has more requests to send, then it will try and use the exact same connection. So you at least avoid the second TCP handshake to do the subsequent requests. On the same connection, the server is going to parse the request, respond, and then if the client sends another request on the same connection, it's going to parse that next request and then respond again. So that's the persistent part of it. And this can be done for as little as 1 extra round trip time for all of the referenced objects in this connection. Okay, so the server overhead is reduced. There's less connection setup time. There's more data transfer. The congestion control behavior is improved because now you have a long-lived connection, and the long-lived connection can probe for extra bandwidth. It can actually grow the congestion window size appropriately to get more bandwidth out of the network without causing all this loss. Okay, the response time is improved because you're getting rid of all the serial handshaking. You don't have to wait round trip times on a TCP handshake anymore. You can just send the request and have it be served. Okay, so they created these 2 request headers for controlling this. There's the connection keep alive and the connection close. This allows the client, it's a request header, it allows the client to say, you know what, keep this connection open because I got more I'm going to ask you for later on. So this is an animation of what it looks like. I have the client and the server again. The client does the handshake, sends the request, and some of the handshake is not here, sends the request for content. The server reads it from the disk. That's one round trip time. The client acknowledges it, parses the HTML, realizes that there are a bunch of embedded images, and then makes that request without having to do a handshake. So this is the embedded image request, and then the server gets the image, sends it back, and then the client can send another one from here. Okay, so to show you an example of this, this is a animation, or not animation, this is an output for non-persistent HTTP 1.0. I connect up to this web server on port 80, and I get the base page. I say that's the host I'm trying to get, and then it will basically give me the HTML. It says it's the content type, and this is the payload. And if you look here, there's an embedded image on that server. And in order for me to render this page, I am going to have to, because this is going to close the connection, this is 1.0, it automatically closes the connection, as you see here. Now, if I'm a web browser, I have to parse this HTML, and I have to create another connection to get that JPEG. So that's the old version. This is what it looks like in 1.1. I get the base page. I get this connection keep alive, because I want to see if there's any embedded images. And then I get this HTML page, I see this embedded image in there, and then I will just issue another get on that image, and then the response will come back, and so I've saved another connection setup time. I've gotten two objects in a single netcat connection, and then I can render that. Okay, so that is all fine and good. So this is what we have been using for ages, like maybe 15 years. It's been HTTP 1.1. But HTTP 1.1's got a lot of problems. The first problem is serial delivery of objects. You have this thing called head-of-line object blocking. If I have a file that's in cold storage, for example, and I request, the client has like 4 images to get, and the first image gets blocked because it's swapped out to disk, or it's not in the file cache, it has to like wait for the tape backup to get restored, whatever it is. It's taking a long time. But the other 3 images are in the file cache. I have to sit there and wait for that first image to be served before I can do the other images, because I've asked these requests are one at a time. Like, here's the HTML, oh, get me this image. Here's the image, oh, get me the next image. But I might have 4 images that I want to get. I would like to request all 4 of them at the same time and then just get whichever ones come back first. So that's what you would like to do. HTTP 1.1 can't do that. The protocol is very specific, 1 request at a time. You give me a request, I'll give you the data. You give me a request, I'll give you the data. And if that very first object takes a long time to serve where the other 3 wouldn't, then you're stuck. Then you're basically, your latency on your website is really slow, is effectively what's going on. Okay. Moreover, if you're getting a bunch of images, almost all the image formats right at the beginning give you the pixel dimensions of that image. And for a web page, all you need are those to render a shell. Like, you can start rendering as soon as you know the dimensions of all the images. What you would like to do is say, get all the images, and then have them just start like the old Netscape, have 8 connections, and then you can actually read the beginning parts of each of the 8 images that you requested, and then render the page. So that's another thing that HTTP 1.1 does not give you. It forces you to choose one at a time. Okay, so what you want is the best of both worlds. You want persistence, a single TCP connection. That was valuable. But you also want parallel object delivery. You don't want head-of-line blocking. And that's one of the things parallel connections got rid of, because you don't have head-of-line blocking. You've done all the requests in parallel. So what you would like is some kind of application or object-level demultiplexing within a single TCP connection. I want to say to the server, get me all the images, and on the response, the server is going to say, here are the first 100 bytes of this image, here are the first 100 bytes of this image, and at the application level, I can demultiplex the responses coming back into the actual objects that get rendered. And they could be done in any order. Any order that the server can handle can send me those bytes back of all the images that I have asked for is what it'll send back. So this forms the basis for Google's Speedy protocol, and this was intended to be an alternative to HTTP 1.1. They wanted to replace 1.1 with this, and then it turned into HTTP2. People were like, that's a good idea. We're just going to standardize on HTTP2, and this is what is running. This is what people are trying to move to in the cloud. Okay. So we're now going to talk about HTTP2. What does it do? Two main improvements: multiplex streams, which is exactly what I just talked about, that facility. The other thing that's important is this thing called server push. And so if you're in the full stack web development course, server push is what's going to allow you to do things like single page applications easily. It's going to give you the underlying protocol support for you to make that thing happen seamlessly. Okay, so we'll start first with multiplex streams. So with HTTP 1.1, which is this thing on the left, you have this sequential operation. I ask for an object, I get it. I ask for an object, I get it. So it's pipelined and sequential operation, but you're doing individual requests and response. If you want that parallel delivery of objects in HTTP 1.1, you have to go back to what you were doing before, multiple parallel HTTP 1.1 connections. And so you can do this in your web browser. You can configure your web browser to say, give me 4 to 8 parallel connections. But this is still going to make the server hurt. The server's not going to like this. What you want to do with HTTP2 is to get the same thing without the overhead. So you want one connection and many pipeline concurrent requests. And in this case, in HTTP2, you're limited to 100. So if you have more than 100 embedded objects on your page, then you'll incur another round trip time. But if you only have 100, you can say, I want all these 100 objects. And what happens is HTTP2 will say, give me all 100. And then as a response, the server is going to say, here's this part. This is the object ID. This is the part of the object ID that these bytes correspond to. And then it's going to be able to deliver you parts of every single object as it's available for the server to send. Okay, this is much more efficient on the server in terms of the connections that are going through versus what you would do here. All right, are there any questions about that? Because that's sort of like the main crux of HTTP2 that I see. So the ID that it uses are stream identifiers. So every time you ask for a set of 100, each object of that 100 has a stream identifier associated with it. And then on the response, the server is going to say, this is the stream identifier, and this is the byte range for the object that you're requesting on that identifier. And then that allows the client to reassemble all that data. So that's what it is. Server is going to label all the data coming back, but that allows you to bypass this head-of-line blocking on the server. Okay, so it's an application-specific solution to really a transport protocol problem is what I view this as. Okay, so as a demo, you can bring this up on a web browser, go to this Gopher tiles thing. It is an HTTP2 server written in Go, trying to render so the Go language has a Gopher icon. So there's a Gopher icon that's tiled, and it's tiled, I think there's like 100 tiles. And if you get that image using 100 HTTP 1.1 requests and response, you're going to get all those round trip times. That's done serially. And then when you click on the HTTP2 version, whoops, there is one connection, and then all 100 tiles are requested simultaneously, and then you'll get the multiplex stream coming back. So this is what I want you to see. And so before I show you this, one of the reasons a lot of these website development, you'll see this in the full stack course, you take all your assets and you compile them into a single file. The reason you do that is because the transport protocol sucks. Right? Like you have to put everything in a single file because you got all this head-of-line blocking going on the transport protocol. One of the nice things about HTTP2 is you don't have to do that anymore. I don't have to like compress I don't have to take all of my CSS and my JavaScript and create one enormous file out of them, compile them down into something small and then ship that in my website. I can actually leave the thing in a readable format, and the transport protocol is going to take care of the demultiplexing for me That's what you want. And so this actually does change how people are going to deploy web apps in the future, I think, once this is ubiquitous. This is not ubiquitous yet. So what I want to show you in this page, if I click on it, hopefully it's up. So this is what you're looking at. This is a little the Golang mascot. And there are a bunch of links here that allow you to retrieve this tiled image using a specific protocol version, like HTTP1 versus HTTP2 on the left, and a particular latency. So if I click on HTTP1 and a 200 millisecond latency, you're going to have to wait for 200 milliseconds for each of these embedded images. So that's what this will be. And you see it's doing these things one at a time. It might be high bandwidth, but it's doing them one at a time. And then the same thing for HTTP2 using the same latency. And you can see it renders all of that, all on a single page, and then you get the objects back much faster. Okay, so HTTP2 is something that we should be moving towards going forward. Are there any questions about what's going on with HTTP2? Okay. The other thing that's being used is server push. So one of the things with HTTP 1.1 is that the client has to fetch the origin page, has to go there and parse the HTML, and then when it realizes it needs an embedded object, it has to make that request. The server already knows what embedded objects that client's going to need. So why isn't the server doing anything? Like the server could be pushing me the embedded object. So when you have a single page application, so in a single page application, you send them one big package, and then as they need the content, you sort of like push that content towards them as they might need it. And so the key thing with a single page application is that you don't want to have to ship all the content up front. Right? It has to be low latency. So you ship them just the amount to render that base page. And then what you're going to do in the background is start pushing the assets for all the subpages in that single page application. And that's done with server push. So this allows the server to say, you know what, I want to populate the client cache in the web browser with objects that I know this application is going to eventually need. So as long as you have a session on my site, I'm going to be pushing you stuff that I know you're going to need so that when you go click on that link in that single page application, hopefully it just shows up, right? Like I don't have to go over the web to get that asset. It's already there. And so that's what this server push is about. And that's HTTP, part of HTTP2. So again, you have this round trip time. It sends you the base sort of page of the single page application. Oh, this is the old way of doing it. So you parse the page, and then you subsequently request the embedded objects. This is what you want to have happen. So this is what server push allows you to do. You want the server to be able to preload that content directly into the browser cache before the client even needs it. Now, of course, this might waste some bandwidth, right? Because you're actually pushing content that you don't know if the client's actually going to need. You're opportunistically pushing it there. But here's what you would get. You would get this request for the base page. It'll send you the base page, but then in the background, it is sitting there pushing you embedded objects to fill out your single page app. So that's what HTTP2 gets you. So you can see this is sort of good, right? Like if you're a web developer, you're like, this is actually what you want. You want a base page that really goes fast, like renders quickly, and then subsequent pages magically also render quickly, and while the person is browsing the base page, you're just pushing the objects ahead of time. Okay, well, there are some issues with HTTP2. That's why we have an HTTP3 coming out. So the story's not quite complete. There is no potential HTTP4 yet, but maybe come back in 10 years and I'll be doing the same lecture and then adding one more version. Because it took at least 10 or 15 years to get from 1 to 2. It took like 5 or 6 to get from 2 to 3. So there are still some issues with HTTP2. There's this initial connection setup that basically what's happening with an HTTP2 connection is that you're still doing a TCP handshake, then you're doing the TLS handshake to get HTTPS, and then you're doing the HTTP request and response. That's a lot of round trip time still, like overall, to get the single base page. You still have TCP congestion control that is your bottleneck, that startup. You also have issues in error correction for lossy wireless links. Like if you're trying to access a page over your cell phone and that last hop is really noisy, you would like to add error correction codes to your packets to automatically add redundancy in your packet so that if there are bit errors in the packet, you can automatically fix them because you can use the redundancy that you have added to the packet. And you want that to be adaptive, right? Like you don't want to put this redundancy on a fiber network link. You're like, there's no errors there. But on a wireless link, yeah, you want to add some redundancy so that you don't lose the whole packet if one bit gets corrupted. So that's what that you would like in HTTP, some support for doing error correction. I actually don't know if this is going to make it to HTTP3, but that's what they jammed in there to try and get standardized. The other thing is TCP connections are bound to an IP address. I didn't really go into this in detail, but if you look at that identifier, it's the source IP address, the destination IP address, and then the 2 port numbers. If for any reason you change IP addresses, that connection gets torn down. And so if you go from 4G to Wi-Fi, like that connection gets blown away. And so you would like for the connection to survive regardless of the network you're coming in on. And so they wanted this is a transport layer issue because the transport protocols right now are completely wiping the thing out as soon as the IP address changes. So you would like to bind a connection to the browser session, for example. So that just as long as it's the same browser interacting with the back-end website, you have the same connection. So that's an issue with HTTP2 that needs to get fixed. And this motivates Google's QUIC. So this is QUIC, which is now HTTP3. Oh, I got time. I got 8 minutes to go over QUIC. I'll go over it quick. So QUIC stands for Quick UDP Connections. This is a reliable multiplex transport over UDP. It's always encrypted, reduced RTT times, runs in user space, and is open source. This is Google's rewrite of the web protocols to improve performance. And what they did was they were like, this IETF is a debating organization. We don't really want to get involved. All right. I'm not talking to you, unfortunately. So they decided to they own most of the browsers and they own most of the websites. So they're not, we're just going to deploy this and show that it works and then ask them to standardize it. And lo and behold, the strategy works. They built this, they showed that it worked, and now it's going to be HTTP3. So why did they do this? So the problem with the web is that you have you have the browser, you have the protocols, and then you have the physical network to get to your site. So what you would like to do is squash this. Like you want the thing to be super fast. And so what they have done, I'm trying not to say the G word. What they have done, they have built out this content distribution network. Now they have sites right in your back door to solve this part of the delay. So they have a carrier-grade network. They've also done this. They have their web browser, and then they built HTTP2. But everything in the middle, this part, this TLS, TCP, and IP, they have no control over. And they have no ability to make that faster. And so the idea, and I said earlier how layering is good, as it turns out, there's this corollary to that thing that says anytime you have layering, you can violate the layering if you want to improve performance. And at this point, everything is running HTTP2. So the idea here is why don't we collapse all of this into a single monolithic protocol? Because everyone is using HTTP to access all the content there. Like all these new applications, of course they're running on HTTP. So the idea is to just optimize this in the middle. And so this is what it looks like now. You have all these 4 protocols stacked. The idea of QUIC is to use the API of HTTP2 and to basically build a protocol that speaks HTTP from an API standpoint. It speaks URLs and HTTP headers and all this other stuff, but in the middle, just completely bypass TLS, TCP, and just put it right over UDP. This means the functions that you would normally have in TCP, like the sort of the segmentation and the retransmissions, all of that's done in QUIC. And then all of the security stuff that you would have in TLS, that's also done in QUIC. Okay, so the idea is that you're going to collapse the stack to eliminate all your layers. And it's basically a single protocol that spans all 3 layers in the stack. And so because HTTP is basically the new carrier protocol for all the network applications that we have, if you optimize it with QUIC, then you're going to get benefits across all applications. Okay, so what does it have? It supports the same thing HTTP2 supported, this multiplex streams and object level demultiplexing. It has the 0 round-trip time connections with TLS 1.3. So after you've established a full handshake with the server, you establish a connection cookie, basically, almost like a session key, so that when you want to get another page from that same server, you don't have to do the full handshake anymore. You can just start sending. So that's what this is. Reliability over UDP, so you don't have the TCP handshake anymore, that the round-trip times associated with the TCP handshake. It does support forward error corrections. It does support connection migration with an IP address change. Now there is a logical connection ID that's associated with your session, rather than having the connection ID be part of your IP address and your port range. It's actually an application level connection ID that it now carries as part of QUIC. And then pluggable congestion control. So you can choose your own congestion control. So if you're going from here to Mars, you might need a different congestion control protocol than if you're going to go from here to your backyard or wherever. So that, I mean, and being able to parameterize a congestion control protocol based on how you're sending, where you're sending it to, is really important. Okay, so here's a picture. Before, you had TCP handshake, and then you had, if you wanted to do TLS, you had the handshake, TCP handshake, the TLS handshake, and then you can do the actual handshake, the actual request and response. With QUIC, ideally, all you have to do is send an encrypted request and get an encrypted reply straight from UDP. So that's much faster. And that's all I wanted to show you there. It also gives you the exact same benefits that you got with HTTP2. So with QUIC, you're just sending, so all of these different colored segments, they all belong to a particular object. So the blue segments go to a blue object, the red segments go to a red object, and so on. So QUIC allows you to just send all of those segments in any order, and then the reassembly will happen on the client, the mapping back into the object. So it does something similar to the other, to the HTTP2. Okay, so the connections, specifically, it's UDP with encrypted and authenticated packets. One of the things that's nice about using UDP is that it prevents any of these NAT devices from working. It disables them, actually, because it's an encrypted payload that it can't rewrite the packets for. Connection ID is a 64-bit UUID. 2 minutes. I'll get there. In terms of establishing a QUIC connection, you basically can send the same HTTP. You connect up to port 80 on the UDP server, on the server, and then it will ask you whether or not you want to use an alternate protocol. And if it supports QUIC, it will give you this header, and then you can just speak QUIC to the server. So that's how the incremental deployment works. So you can ask the server if they support QUIC and then start using it immediately. Okay, so they did like if you, there's a paper that talks about the performance speed up, which that's not this link, but places like Uber are employing QUIC for their web clients, and they're getting good results. This is the deployment at Google. So underneath, on all of your YouTube apps on your phones, you're doing QUIC to their backend automatically. And so you see the QUIC traffic here in green, and you see that it's now a dominant portion of Google's backend network. So this must be at least 50% now of their traffic. Okay, your lab is going to have you look at QUIC. So this is a picture of being able to get to the statistics in your web browser to pull out the QUIC statistics. And in Wireshark, you can see that Wireshark has been updated to be able to understand QUIC. And this is being turned into HTTP3. This is from last year, November of 2018. So this will be standardized and people will be adopting this really soon. That's where I'll stop. See you next week. Yeah.